Okay, thank you. Okay, so in this last talk, I'm planning to finally mention. So I will talk about how this kinds higher derivatives of L function arise. So the topic of this talk will be about this Clifford algebra. And I think in the previous talk I draw too many diagrams, and maybe many of you are tired of it, and I think the content of this talk will be mostly independent of the previous talk. So I think if you don't follow every detail of the previous talk, I think it will be fine, and I will. So I hope no. Yeah. Okay. So maybe let me still start from recap. Oh, okay. So I consider this group pair GH, GLN minus 1, and GLN cross GLN minus 1. And X is G mod H. And I fix the local system sigma, which is a tensor product of 2. That is geometrically irreducible. And I don't write it again. And I have this Hecke eigensheaf L sigma, which is tensor product of Hecke eigensheaf for GLN and for GLN minus 1. So sheaf on Wang G. Okay, and so from this you can consider map pi from Wang H to Wang G, and you have the Pierre sheaf Px, which is a lower trig of the constant sheaf on Wang H, and so consider this functor integrate using x, which is just take first tensor with Pierre sheaf and take convex support homology. So it's a functor defined on sheaf of Wang G. And okay, so I have this two choices of co-weights. Here it's some co-weights of H regarded as a co-weights of G as well. And so we also have a mu minus. And so for each choices of signs and degrees, so you have a map between Shtukas, pi Shtuka from Shtuka H to Shtuka G. Okay, and you have this special cycles. Okay, it's a push forward of fundamental class of Shtuka H. Okay, and we somehow only care about its sigma isotypic part. So what is that? You just restrict this special cycle. So recall that it's a covector in this middle dimensional compactly supported cohomology. You can restrict it to the sigma isotypic part. Which is isomorphic to the cohomology of the local system tensor to some power. And okay, so here I'm just assuming this Shtuka moduli space are non-empty. So you're not considering something stupid. And So recall that in the statement of the main theorem, so I need to put all these special cycles together. So you sum over all degrees and all this sequence of signs. And that's some element inside the dual of the isotypic part for all these choices of signs. So let me introduce. M is the cohomology of the local system, and direct sum is the cohomology of the local system, and take dual. So this is really an element lies in M tensor R and dual. Yeah, because if you write M as a direct sum and expand this tensor product, you will just see all this sigma isotypic part. So this special cycle really lies here. And okay, and I want to use W to denote this this cohomology. So M is W, direct sum is W dual. Okay, and so recall that you also have this this intersection pairing. So it's a bilinear form. It's a bilinear form defined over. It's a bilinear form on this M tensor to the R, to QL bar. But so we want to show it's non-degenerate, and once it's non-degenerate, you can pass to the dual form. Dual. Okay, so you have this form, but that's not given. You need to show it's non-degenerate, and the theorem we want to prove. So the target theorem. So it's that. So if you so if you're considering, so if you pair the sigma isotypic part of special cycle and sigma star isotypic part of the special cycle, you will get, so you will get some not very important constant times. So the most interesting part is this R's derivative of this L function as a central value. And less interesting, but still interesting, which is this residue of a joint L function. Okay, so this is what we want to show, and okay. And so now I want to recall you more things, but okay, but this already goes to the section 1 that I prepared, and I want to use some horrible names for the title, which is called L observables. I think it's a name. It's a name appearing in the PDSV paper, and I will explain what it is in a moment. This is still part of recap because you have already seen this L observables actually last time. So recall that we constructed two maps. So we have constructed two maps like the following form. So from M tensor R, tensor with this geometric version of pure integral, to this geometric pure integral. So this map, I think last time is denoted by A epsilon, but now I'm summing over all epsilons, and I just denote it by A. and its construction, okay, so the construction I gave last time is via categorical trace, but the that construction is, okay, it's not given via categorical trace, it's just given via natural transformation, but the construction is very explicit, and I will recall very soon. But this map A will satisfy the property is that, so suppose you take the trace of Frobenius and compose with A, then this will give your special cycle. This is VR sigma as an element inside M tensor R dual. Okay, so my notation here may be a little bit confusing, but okay. So this composition is another map from this to this. And what does it mean to take trace? It's okay, so taking trace is a procedure that you can cancel this pure integral and pure integral. I mean, the trace is taken over this. So the resulting thing is a map from this tensor product to the trivial vector space. So I think that should explain the meaning of this traces, just some elementary operation on the finite dimensional vector spaces. Okay, so so we have this map A, and we have another map B. I didn't write down because I assumed that so you can use the same method to study the intersection pairing, but via that's true. Via similar construction, you will have map B, which recovers the intersection pairing. Okay, so you have a map B from this to this. To this. Okay, so you will have such a map B, such that the trace of Frobenius composed with B will be the intersection pairing restricted to the isotypic part. So, and now I'm going to remind you the definition of A. So last time I constructed in abstract way, so maybe you will feel a little bit confused, but it's actually quite explicit. So how is A constructed? Okay. So I think last time I construct this A epsilon underline, which is a map from H1 sigma tensor to the epsilon's power and times this integral to the integral. Okay, and so A is just a direct sum of all the epsilons. Okay, so how this is constructed? Okay, so the first step you just write down the definition of this pure integral. So it's that you first tensor this eigensheaf with the pure sheaf and take compactly supported cohomology. And then you realize that, so this L sigma is a high eigensheaf. This is really the so-called high eigenvalue of this eigensheaf. So you can absorb this thing into a Hecke operator. So it's really just, so you apply a Hecke operator that is indexed by this co-weight and apply to the Hecke eigensheaf and tensor with the pure sheaf. Okay, so this is the first thing you do, and this step really corresponds to the, so I think last time I constructed a natural transformation called 1. This is the 1 there. And okay, and then you realize that, so this Hecke operator is kind of self-adjoint, and you can use this adjoint property to move from L to P. So, but for that, we need to pass to the dual representation. Yeah. So you do this, and then well, then you see that this pure integral is just compactly supported cohomology with a high eigensheaf tensor with a pure sheaf. So to construct this A, you just want such a map, and such a map is given by so it's provided by such a map. So it's a map from this Hecke operator applied to the pure sheaf to the pure sheaf. But potentially there's some shift, and okay, so there should be shift everywhere where they just ignore. Okay, and this map is just it's just induced from this thing. And this is the data for cohomological correspondence. Oh, okay, but I think the okay, and so I draw lots of diagrams for cohomological correspondence last time, and the purpose of those diagrams are just to construct this element. Yeah, so. But here, at this moment, you can just think of this as something given, and let's try to. Which one? Sorry, can you say again which one? On the bottom?
No. Yeah.
Here?
You have a comma.
Sorry. Yeah, okay. Here's it, yeah. So, well, so that's the construction of A. And if you don't like the cohomological correspondence stuff, just take this as the input. Yeah. So now we try to see how the theorem can be true. So, well, then you note that. Okay. So there seems to be two pairings on M, and one is that one given by intersection pairing, but M itself is so it's W plus W star. So itself carries a bilinear form. So note that this M is just W direct sum with W star, and it carries a natural carries a quadratic form. And let me just use this to denote this quadratic form. And right, so you can actually refine this. Theorem. So you can actually refine the theorem by separating it into two statements. So the first statement, I want to call it A Shtukas. So sorry for the weird notion. So is that let me think about what should I write. I should write this. Sorry, I really should write this. Okay, let's put sigma du here. So, okay, so you can pair the sigma isotypic power with sigma star isotypic power under this U quadratic form. So it will be a constant times the R's derivative of this L-function. Yeah, so this is the first statement. The second statement is really a comparison between this quadratic form with the intersection pairing. So which says that the intersection pairing is so it's mostly the same constant times times this residue stuff. Yes. So this really separated the theorem into two statements, and right. So you can think of the first statement as a statement about so as something vertically normalized, and the second is purely about the. Oh, yeah, sorry. Yeah, right. Yeah, right, the pairing should be. Thank you. Okay, so I want to call this theorem Shtukas because later there will be a theorem which is not about Shtukas and imply this one. So, okay, so yeah. So you see that okay, so to prove this theorem, you really want to understand this map A and B. And actually, that's the only thing you need to understand, because once you understand them, you take trace, you know what are these two things. So, right. So our goal is to understand A and B. Okay. Right. But there's one step you can make some simplification. So note that what really is the map A. So you can think of A as a map from the free tensor algebra of M to the endomorphism ring of this pure interval. Well, so this is not just an empty statement about that map. It really means the following. So it means that A of M1 tensor M2 well equals to AM1 and composed with AM2. Yeah. So I'm saying that if you write that map in this way, so it will satisfy this associativity. But that's something not hard to say, not hard to see. It's just follow from construction of A mostly, and it's not something deep. And you can use the same way to understand B. Okay, so because of this associativity, you can assume. So to understand A and B, you can really assume that the number of legs is 1. So you can make this assumption. And okay. Yeah, so then what's really the data of A is? So A is really such kind of data. So it's a map from W direct sum with W star times this pure interval to the pure interval. Well, but I think in the so in my first talk, so you have already seen this result of Lysenko. So he can really compute this thing, And this is just the exterior algebra of W. Yeah, this exterior algebra of W. So you see that A is really such a map. And for B, okay, so you can actually enhance B into a more refined version. So you can refine B into such a form. Okay, so okay, since the group is GLN cross GLN minus 1, let's just study the group. Study one part of the group, which is GLN. Okay, so you can refine B into such a map. Sigma n tensors sigma n star, and map to constant sheaf on the curve tensor with L sigma times L sigma n star. So let me call this map B tilde. So in what sense this is a refinement of B? Okay, so now I should say that both objects now are really sheaves on the curve. Yeah, so why I make this refinement? Because you see that the intersection pairing, so you can define it over the entire Shtukas cohomology, but there's a refinement which is you can take intersection fiber-wise. So it's really a bilinear form on the cohomology of Shtukas as a local system over the curve. So I make this refinement, and so in okay, so in precise sense, how this B tilde refines B. So it's given by, so you can take the cohomology on the curve to this B tilde, then you will get the cohomology of sigma n tensor with sigma n du, and tensor with this stuff to the cohomology of the curve tensor with this stuff, and this thing will receive a cut product from gamma n tensor with gamma n du, and this thing will has a fundamental class mapping to just QL bar shift to cohomological degree 2 and tensor by the same stuff. And you see that, so here it's a cut product, and here's a fundamental class. And this composition will be our original B, but for the group GLN rather than GLN cross GLN minus 1. Yeah, so you all see some advantage of considering this refinement very soon. Okay, so now I'm going to state a theorem. With no superscript Shtukas, which means that it's independent of the Frobenius. So there are still two statements A and B, and so A is about a description of this map A. I think you can already guess what this map should be. Okay, so you how can you construct the map from this to this? Well, we don't have much natural choices. I mean, so the map A will send so W tensor W1 wedge to which one? W1 to WK. So A will send this to just the multiplication. Okay, and that's how W acts on this exterior algebra, and how W star acts on this exterior algebra is just given by differential operators. It's given by alternating sum. Okay, so it's just the most natural action you can think of. Okay, so So I want to think of this as applying the differential operator W star to this function W1 weights to WK. Okay. So yeah. So this says that this action map is really just the action by differential operators. And the second, okay, about B. So I want to describe this map. So it turns out that, so if you want to study the entire map B, tilde is not very easy, but you can study a stalk at some point on the curve. Okay, so I should say that, so for any point on the curve, then I can study a stalk. So the stalk of B at the curve, at the point is really the same as, okay, so what's the most natural map you can think of here? So just ignore this factor, and there's a natural map from sigma n tensor sigma du to the constant local system. Okay, so that's a co-unit map for the local system sigma n, and you restrict it to the point, and you just tensor identity. Okay, so that's the second statement. And okay, so of course this, okay, so the co-unit is just this most obvious map. Yeah. So that's a more refined version of the theorem Shtukas. And I claim that if you take trace for this theorem, you will recover that theorem. Okay, so any questions so far? I think now I'm going to explain to you how can I use this to recover that. So okay, so if there's no question at the moment, I can first explain how can I use B. How can I use B to deduce B Shtukas? So in particular, this should prove the non-degeneracy of the intersection pair. So, okay, so it's via the following way. Okay, right. Okay, so you take trace of this and compose with Frobenius, and see what happens. So you consider trace of Frobenius, compose with this B tilde, but as a stock C. Then you will get this identity, composed with a co-unit map. Okay, so here I'm doing nothing, just take Frobenius trace of this. Okay, this element will be some morphisms from the stock of this local system at point C to the vector space QL bar. Right, and okay, but what I really want to study is stock, so it's the trace of Frobenius and composed with B tilde. So this is what I really want to study, and I want to compare it with this easy one, Frobenius composed with co-unit sigma n times identity. So okay, so I really want to compare these two. So it's a homomorphism from sigma n tensor sigma du to the constant local system. Well, but you see that here I can say that I'm not ignoring any shift because that's important. Yeah, here it's really Hom. Here this Hom is really not derived. So let me write Hom 0 to emphasize that. And so the operation of taking the stock at C really induces isomorphism. Okay, so from this identity on the stocks, you really that really implies that these two traces are the same. So okay, so that's how you use B, and then this will imply that okay, so since now you see that this map is really something very simple, and the Frobenius part and the co-unit part are actually independent to each other. So this implies that the intersection pairing is just the trace of Frobenius on this geometric version of L2 pairing, and times the standard bilinear, the quadratic form there. Okay. So right, and you see that. So this really implies the statement GShtukas. Okay, so that's how you deduce the non-degeneracy of the bilinear form. Okay, and any questions so far? Yeah. Okay. So suppose there's no question. Let me now let's come to the more magical part, which means how can you deduce a statement about higher derivatives? Yeah. So okay. So I think for me it's a magic. Okay. So it's how you deduce from A the statement aix-Shtukas. Well, should I say it's a linear algebra exercise. Yeah, because everything is already explicit and you can compute. But that probably that's not a very satisfactory answer. So I still want to do this linear algebra exercise on the board. Yeah. But okay, so maybe that will be postponed to later. So now let me remind you what we need to do. Okay, so first, so we have the following question. So first is that how to prove A and B. This is the first question, and the second question is, of course, why you have this magic? I mean, okay. So it turns out that both questions have the same answer with this because of the Clifford algebra. Okay, and of course, so for A is Clifford algebra, but for B, I'm not going to explain. So I'm not going to explain later in detail, but it's the symmetric version of Clifford algebra. I mean the wire algebra. Okay, so that should be the answer. And but this is not precise. So so precisely, what do I mean? Okay, so precisely. Well, so you see that you have a map A from M tensor to the endomorphism ring of this pure integral. Well, how Clifford algebra appears is that, so I claim that this action map will actually factor through the Clifford algebra of M. So, okay. So precisely, I mean the following. So recall that how you define the Clifford algebra is M tensor quotient out by some relation generated by M1 tensor M2 plus M2 tensor M1 and minus the pairing between M1 and M2. You take quotient by this two-sided idea. Okay, so that's what I mean by the Clifford algebra stuff. So, right. Oh, okay. So maybe yes. Yeah, because I choose some geometrically reducible local system. Yeah, right. Yeah, right. Oh. Okay. So the other, okay, sure. Sure, I think, yeah, so roughly speaking, so A is responsible for Clifford algebra action, and B is responsible for a part of a wire algebra action. And if you want to see how that wire algebra action comes from, so it really comes from, okay, so B is used to study this intersection pair, and it's a diagonal, it's a group case. And for GLN group case is somehow like a residue of the equal rank Rankin Selberg case, and that's still a strongly tempered setting. And in that setting, you still have a Clifford algebra thing, but with a shift, and the shift make it a wire algebra. Yeah, so that roughly explains what works for B. Yes.
May I ask? I should have asked it earlier, but you said you can assume that R equals 1.
Yeah. Oh.
Can you say why?
Oh yeah. It's because this A is really algebra homomorphism, which means that it's associative. That mostly follows from construction, and if I really want to explain that, I need to draw lots of diagrams. But yeah, it's written there that A of M1 tends to M2 is A M1 composed with A M2. Yeah, that's the associativity of A. Yeah. Okay. Thanks for asking. Okay, and so now this is the precise statement. Let me call it a box. Okay. Right. So now I'm going to explain a little bit why a box implies a circle. Okay, where's a circle? Oh, it's there. It might looks obvious to you, but let me still explain a little bit how this works. Okay, so you see that this geometric pair integral. Okay, so now you are considering GLN case, and there's a grading. There's a grading given by the degree of the vector boundary. This pair integral split into a direct sum, where the degree D part corresponds to taking compact support cohomology on bound H. Degree D part of pi upper star of the eigenshift. Okay. And what really okay, so what is Lysenko's result? So Lysenko's result, okay, so it really tells you that so the degree D part of this pure integral is okay, so it's isomorphic to some specific power of exterior power. So it's really this. Okay. And in particular, this implies that so the lowest degree term, the lowest degree term. So it's really one-dimensional, right? And then you can pick any element C0 here, and okay, so what does A box tell you? So A box tell you that Okay, so if you consider the map from W tensor to this pure integral, by what? By sending an element, say W, to, okay, so you apply the operator W to the element C0. Okay, so recall that W is regarded as a subvector space of M, and you can, and M acts on this, so you can, that W acts on this, and you can act on this element C0. Well, and so the relation of Clifford algebra 0 will tell you that these operators commute with each other, so it will factor through the exterior algebra of W, right? And also, so the other part of the Clifford algebra will give you some differential operators on this, and that will forces this map to be injective. Right, that forces this map to be injective, but if you consider dimensions of both sides, you see it must be an isomorphism. And I should say that similarly you can deduce B. Similarly you can use some B box to deduce B, but okay, but well, not. Okay, so it's, yeah. Okay, so now I need to point out a subtle point in this thing is that, okay, so a priori, so you may think you want to prove A by just see what Lysenko's proof gives you. I mean, Lysenko's proof will give you an isomorphism here, and you may want to trace how this kind of cohomological correspondence stuff does in that under this isomorphism. But I think I tried this for GL2. I think it's mostly fine, but I guess I'm not patient enough to do it for GLN. So, but using this Clifford algebra stuff, you see this is the so you can actually choose another isomorphism from this pure integral to this exterior algebra, which is this map. And so under this isomorphism, it's clear that this W acts via the following way. So in this theorem, I'm actually cheating a little bit. So yeah, so isomorphism between the exterior algebra and this pure integral is really this one that I constructed here. Okay, so that's one of the subtle points. Yeah, so, okay, right. Now I think I'm ready to yes.
I don't understand because
Oh, yeah.
you're saying that this follows from A.
Oh,
To
oh.
formulate A, you need to have a representation.
I need to have what?
Representation of your space as an exterior algebra.
Sorry, you mean A square or A circle?
So the statement A.
Okay,
You use it to identify
Hmm.
the vector space to the exterior algebra of W.
Yeah, right. Yeah, that's right.
Using the identification in the, you're also using the identification in the state from the space. So
In the state. Okay, so yeah, right. So yeah. So I think maybe I can really say that. So the A circle here should be really saying that this is an isomorphism. I think that's a more accurate statement for A. Yeah, but that is sufficient for our purpose. Yeah. Right. Yeah. Right. So Okay, so that explains how to use this Clifford stuff to prove A and B. And now the second question is, how do you do the linear algebra exercise? Okay. Yes. Oh, yeah, second relation. Oh, that follows from the Clifford relation here. Yeah, that follows from this relation. Yeah, remains to be proven. I mean that A box has not been proven. Yeah. Yeah, right. But in this procedure, I'm still using the, say, for example, this is non-zero and this dimension is the same as this one. Yeah, that's all I need. Right. Yes.
In the statement of A,
yeah.
the pairing of the two is just it's the round pairing from before, right?
In the statement of GShtukas, right? Yeah, right. I think that's the content of B. Shtukas says that the intersection pair. Yeah. Okay. Thank you for asking. So now let's go to section 3, which is this. I don't know how to call it. I think it's magical, so I call it magical linear algebra. Okay. And the setup is the following. So you see that you have an M, so which are quadratic space. And so it's an even dimensional quadratic space. Well, and you have an endomorphism of M, which is F. So in this setting, it's given by the Frobenius. But you see that this quadratic structure is very natural, so that the Frobenius lies in the orthogonal group of M. And now you see that M is acting on something which is the geometric pure integral there. So that gives you a S. So S is a irreducible representation of the Clifford algebra. Well, but you can also and this stuff is Z2 graded. So I mean it's even Z graded in this setting. Suppose you have a Z2 graded thing. And you see that this geometric pure integral also carries a Frobenius here, so which is an endomorphism Fs, such that these structures are compatible. And so from this module you have the action map for the module, which is a map from M tensor with S to S, and it's the same as a map from M tensor to endomorphism of S. Okay. Yes.
Is there a section 2?
Is it? Oh. Oh, sorry. This is section 2 in my notes.
The other question is, what is the thing that you call, or that they call L-observables?
Oh, what is called the L-observables? I think, okay, so strictly speaking, this, the action by this element W and this W star, the endomorphism on the pure integral coming from this M are called L-observables. Yeah. So you see that this is something like states, and this is like observables in some sense. I don't know. Okay. So, okay. So from such a data, you can define a sequence of elements ZR So Lycee M tensor to R due. And it's defined as just by taking trace of Fs composed with A. Well, oh, sorry, A is here. Okay, then what happens? Oh. Okay, so then here's a purely linear algebra statement. Well, I think it's first observed by Zhang. And I think and it's slightly and it's reformulated into this form in our paper. Okay, so which says that so this M ZR pairing with itself, well, is some constant. Well, so this constant can't be made can be made explicit, but I will do that times times the R's derivative at 0 of the L function. In this case, it's the characteristic polynomial of f in the following form. But let me remind you that you need to take this normalized L function. So you need to put a factor here. Okay. Yeah. So this is the linear algebra stuff. And I probably don't have time to say the history about this. Maybe let me first finish the proof of this. Okay. So although it's linear algebra, but I think it's very so for me, I think it's it really explains why you consider this intersection of special cycle stuff. You can get a higher derivative of L function. That's something like very mysterious, but that's explained by this linear algebra theorem. Okay, so how do you prove this? So you consider so you can consider M direct sum with M, and with the obvious bilinear form here, by declaring that these two vector spaces are orthogonal to they are orthogonal. Okay, then the Clifford algebra of M direct sum with M. So it's the same as the Clifford algebra of M, tensor with Clifford algebra of M. And you see that this acts on S tensor S. This acts on S tensor S via the action map A tensor A. Well, so so far it's just trivial, and this is still irreducible, still an irrep. And so since M is a quadratic space, you have a unit inside M tensor M. Okay, and so what are these elements ZR? There are some dual elements inside M tensor R. Okay, so how do you actually compute the pairing between ZR and ZR? Well, so it's really just, okay, so you can write it in the following form. So you consider ZR tensor ZR and pair it with unit tensor to R. right? So because this Lyceum M tensor R dual in tensor with M tensor R dual. And this Lyceum, well, no, M tensor M to the tensor R, and these two spaces are really due to each other, and you can make this pairing. Well, but what's the advantage of this? Because this ZR is defined as a trace, so if you write it in this form, it's really just you use the action map A tensor A, and you apply this to the element unit, and well, and you can do this R times and compose with the Frobenius. Okay, so in this case, it's just some endomorphism on S tensor S. Well, so you write this pairing via a trace. Right. Well, but okay, so write this pairing as a trace on S tensor S. Yes. So, well, but then you see that S tensor S is something very explicit. You can make it very explicit in some sense. So there exists an isomorphism from S tensor S to the exterior power of M. Well, that's because now this M direct sum with M carries an obvious polarization and its unique irreducible rotation. So there's a unique one. It can only be this exterior power. And there exists such an isomorphism as module for the Clifford algebra. Well, but the problem is that the endomorphism may not match. But you see that since here you have, okay, so here you have a natural endomorphism that is induced from the endomorphism on M. And here you also have, and these structures are compatible. And that's really strong requirement. And once you have this, it will forces the endomorphism here will be a constant times the endomorphism here. Well, so that's something you can check, and I think it's, yeah. So, okay, so now what's the key point? Okay. Oh, and I should say that this constant is responsible for the constant here. Well, and you can make this constant more explicit in terms of the spinor norm or something. So, okay, so the key point is that, so now you see what you need to compute. You need to compute the trace of Frobenius here, composed with the action by an operator called unit. So the key point is that, so this unit acting on this exterior power, so it's a differential operator. It's a differential operator of order less or equal to 1. Well, so that's somehow the key point here, but okay, so I should say this this is really a simplified summary, and so just this statement is not enough to imply this one, but I think it summarizes the key feature here. Okay, so but that's just a summary. Let me let me complete. Let me complete the proof. Oh. Yeah, okay. Okay, so okay, so let's pick. Okay, so now I'm going to do some do the only explicit computation in my talk. Well, so now I choose the orthonormal basis of M. Okay, I choose the basis, and you see what is this unit? The unit is the sum of EI tensor EI, and want to compute its action on this exterior power. And how it acts, so the action is via the following. So once EI acts via, sorry, I'm using J here. So EJ acts via, so the product with EJ plus this differential operator along the direction given by EJ. Quotient by some factor, not so important. Okay, so you see this thing because, okay, so okay, so that's just the action, and this is really equal to I times something like from J to 1 to K, and EJ from EJ, and this sum minus K over 2. Well, so that's what I mean by this unit acts by a differential operator of order 1 and plus something of order 0. And you see that this operator is very simple. It's just a gradient operator, and this is some constant. And this gradient operator is responsible for the R's derivative, and this constant is responsible for the normalization of the L function. Where is it? Okay, it's there. Okay, I see. Yeah. So, right. And the remaining things are just more or less straightforward. So I'm not going to say. Oh yeah, right. Exterior multiplication. Yeah. Let me write here. Yeah. This is contraction. Yeah. Right. Exactly. Right. So. Okay. So this finishes the proof of the linear algebra stuff, and so I still want to make some remarks about this linear algebra stuff. So I think this sequence of elements ZR is actually very interesting, and it's first discovered by Yun Zhang, and I should say that everything in this remark is due to Yun Zhang. So this is uniquely characterized by some properties. By the following properties, which is that, okay, you have this ZR, and you can consider an operation that you swap the I and I plus 1 factor of it. So what's the meaning of that? It means, okay, ZR is the element of the form, okay, so on the ith position and I plus 1's position is of this form. So swap, we'll just swap these two factors. Okay, so that's swap. And if you consider this thing and plus with this swap, it will be a unit tensor with ZR minus 2. And so this unit is some element like m star tensor m star, and this is something like in m star tensor to the r minus 1 power. And this is always true. And the second is that, so there's an operation on this M tensor called the partial Frobenius. This VR is stable under partial Frobenius. And what do I mean by partial Frobenius? It means that you send this element to FMR and tensor with M1 and tensor with what? So yeah, so just do a cyclic permutation, but make a twist by F. And that's what I mean by partial F. Okay, and this sequence of elements is uniquely characterized by these two properties, up to scalar, up to scalar. And this is actually the initial formulation of Zhang of that theorem. Well, so I think they gave this sequence of elements the name under the Kolyvagin system over function field. System over function field. Yes. Well, so it shares something in common with Kolyvagin systems, but I guess I don't know much about this, so I don't have much time left, so I choose to not go into this. Okay, and yeah. Now I'm. Oh, I should not erase. Okay, so yeah, so now I want to explain this. So how do you actually prove this statement A box? So I don't know how to. Okay, so it's this Clifford relation. Yes, okay. Well, so recall that your M is H1 sigma direct sum which H1 sigma do, and it acts on this period integral, and you want to show that relation there. So let me call this relation star. So you want, okay, so you want to show this star. Oh, sorry, I want to call it star sigma to emphasize that it's something happening on the sigma isotypic part. But recall that, okay, so how do you construct this? Yes?
Another quick question.
Yeah.
Star sigma is the same as A bar?
Yeah, exactly. Yeah, yeah, right. It's just, okay. Yeah. Okay. Want this equivalent to okay. So so recall that okay, so let me call this action by A, and you see that A comes from a homological correspondence. The homological correspondence is so it's a data of this kind. So it's a hom from a Hecke operator applied to peer sheaf to peer sheaf. Well, and you have two such homological correspondence, C plus and C minus. Oh, well, but you see that A is about so okay, so this sigma, okay, so this star sigma is really about composition of two such homological correspondences. So you try to compose these two. Well, and you can compose these two cohomological correspondence to get a cohomological correspondence of this form, and I think this composition was previously denoted by this, but it's okay. But there's a notion of composition of cohomological correspondence. Okay, there's a obvious version of composition if I write it in this way. Right. But you see that these two Hecke operators commute with each other. So this Helm space is the same as you can commute these two Hecke operators. But in this space, there's another cohomological correspondence, C minus composed with C plus. Well, but there's a third way to write this Helm space, is that you can use the adjoint property of Hecke operators, and you can make this Hecke operator, make it there. But now, in this way of writing, there's a tautological element, which is just identity. And so a theorem, so it's proved in our paper, says that so we have some stupid assumption on the genus of the curve, and I believe it's not necessary. So assume the genus of the curve is not 1, then there's a simple relation between these three. C plus composed with C minus, C minus composed with C plus, and this tautological element. Well, there will be some signs here, but let's ignore those subtotally. So this is what I want to call star. And you see that this statement is not something happening on the sigma isotypic part. It's purely about cohomological correspondence, and it's purely about geometry, you see. And there's no Frobenius theorem. Well, so how do you deduce that Clifford relation in the Clifford algebra? So this implies star sigma. And since I seem to run out of time, let me stop here.
So thank you for this very nice last talk. Yeah. You can have, I think, yeah, you can go up to 55, I think. You should.
55?
Yeah.
Okay, I see. Okay.
If you want.
Okay, then I can say something I think maybe meaningful. Yeah, so I want to say a little bit about the idea of the proof of this theorem. Yeah, okay. So, well, so what's the idea? Okay, so a theorem is about some relation between this cohomological correspondence. So it's a harm from the Hecke operator applied to pure sheaf, to the pure sheaf. But, well, there's a local counterpart of this. So I claim that there exists some local cohomological correspondence, which is from, well, there's some element called delta x in BZS's paper. What's this delta x? So this is really the spherical element inside the local category considered by BZSB, and but I somehow want to work with this version with loop rotation. Well, and what's this Helm space? Well, it's really by the definition of the so-called Planck algebra. So it's a Helm from this representation to the Planck algebra. So what's Planck algebra? Is this kind of inner endomorphism on this spherical on this spherical object, and okay, so you can take this as the definition of this inner endomorphism, and so I think this is so-called non-commutative Planck algebra, and right, and so the right. In the work of Braverman, Finkelberg, Ginsburg, and Trofkin, their work compute this non-commutative Planck algebra. They said this saying is just, well, so, okay, so now it's the first time that I write down this dual side. Well, so the dual x check will be standard tensor standard -1. And right, so this Planck algebra will be isomorphic to some kind of to a graded version of D modules over X check, and so it's defined. Okay, so it's actually a wire algebra. Well, so this is V mu plus. Okay, so it's really just a V mu plus and direct sum with V mu minus, and tensor algebra quotient by some relation V plus V minus minus V minus what V plus and minus H bar times the pairing between V plus and V minus. So here there's some element V plus, there's some element V minus. Okay, so it's really such an algebra, and which is a quantization of the structuring of the hyperspherical dual. So this is the quantization. Well, and you see that this algebra is really some generators with relations, and so I want to call this relation star local. And well, how I deduce this is to start from this star local and deduce the relation star. Well, okay, so I think that's